Dear students, so now we are going to apply the theorem of least work that we discussed in the last video for an indeterminate structure, and we will see how to analyze that particular indeterminate structure or indeterminate beam. So we are considering the propped cantilever, okay, that is a fixed beam with a roller support at the end is called as a propped cantilever, and let there be a point load. Say I'm giving some magnitude to it, say 10 kilonewton is acting at the center of the beam, okay, 2 meter, so 4 meter is the length of the beam, and at the center there is a point load 10 kilonewton, and let the flexural rigidity be constant, that is the beam is made of same material, throughout the material is same and throughout the cross section is same, that is EI is constant. So this is the problem that we are going to analyze. So now first thing what we need to do is we need to convert it into the structure of forces. So I'm converting this into this supports, I'm converting into reactions and forces. So the reactions, what I will be getting is that 1, 2, 3, and at the roller I'm going to have another one. And apart from this, I have the external loading, that is 10 kilonewton. I'm giving some names A, B, and let this point be C. So this reaction is RA, this is HA, and let this be MA. Similarly, this is RB. So now the first thing what we want to do is, whenever we are dealing with indeterminate structures, the first thing is we need to identify the redundant. So redundant is the, so in the previous lecture we have seen what redundant is. Redundant is the reaction that need to be removed to make the structure determinate. We know that this in the case of a propped cantilever, if you are removing the prop, it becomes a cantilever which is a determinate structure. Determinate structure is that structure which can be analyzed using the equations of equilibrium. So here I am considering this RB as the redundant. Okay. So how will we know how many reactions need to be removed to make it a determinate structure? The simplest method is calculate the DS value. For this given system, what will be the DS value, that is degree of static indeterminacy? It is basically R minus E, where R is the number of reactions. In this case, there are 1, 2, 3, 4 reactions. Okay, the value of R is 4. And what about E? We have discussed in the previous lecture. E is the value 3, because for a 2D beam or frame, the number of equations are sigma fx, sigma fy, sigma m, which means 3. So when I calculate this, I am going to get the value as 1, which means I need to remove one reaction to make this given beam a determinate one. So I'm removing or considering this as the redundant. Fine, so just one redundant is enough because DS is 1. So now we have identified the redundant. Now the next part is to apply the theorem of least work. So theorem of least work says that dou U by dou R, where R is the representation for a redundant. So if you partially differentiate the strain energy of the structure with the redundant, we will be getting the value as 0. Okay, so that's what we are going to apply here. So the first part is to get the strain energy. Okay, and what is strain energy? So we are doing a bit of derivation within the problem so that the theory will be proper. So we know that strain energy is given by integral m square dx by 2EI. That is the expression for strain energy. Now what we want is we want to differentiate strain energy with respect to R. So what I'm going to do is I'm going to calculate dou U by dou R. Then what will be dou U by dou R? It will be integral dou by dou R of m square dx by 2EI. Right? So what will this become? This will be, we know that dx 2EI, everything is independent of R. These terms are constants when I'm differentiating it with R. So it's going to be integral dx by 2EI. I can take it as constants, then what we have is m square. So m square is a function. So when you differentiate a function with respect to r, what I'm going to get is, it is m square. So 2m times dou m by dou r. Okay, so this particular parameter dou u by dou r is equal to integral m times dou u by dou r. Okay, there is a 2 here, and in the denominator also I'm having a 2, so they will get cancelled out. So m times dou u by dou r dx by ei, that is the left hand side of the expression. So integral m dou u by dou r dx by ei, and as per theorem of least work I can equate this to 0. So that's how we are going to solve it. So we don't have to calculate the strain energy. Okay, sorry, I made a mistake. This is not u, this is m. Okay, this is dou m. I accidentally wrote u. Fine. So we don't have to calculate the strain energy. We just need to get the expression for m within the limits. So for doing that, we can go back to the strain energy calculation table that we had earlier prepared. That is, this table is ELOM, the same table we are going to use here. So we need to divide it into segments, need to find the limits, origin and the expression for bending moment. So in this particular beam, how many segments are required? So we can go back here. We can see that there are 3 point load locations. So I'm calling this as segment 1, this as segment 2. 2 segments are enough to divide this beam because there are 3 point loads. Now, so I'm considering segment 1. So EI value for segment 1, EI is constant everywhere, so it is EI. Now, what is the limit? Okay, so first I need to decide what the origin is. When I consider the segment 1, okay, so what I will be doing, I'll be taking a section within segment 1. Okay, a section within segment 1 is section within segment 1. So I will be having the section somewhere here. So either I can look to the right or look to the left for getting the expression for bending moment. If I'm looking to the right hand side, I am having just one force. But if I'm looking to the left hand side, there are a lot of forces. Okay, so the best thing is to look to the right. So I can keep this as the origin. Okay, so the origin I am considering point B. If B is the origin, segment 1 is from 0 to 2 meter, right? 0 to 2 meter is segment 1. So 0 to 2. Okay, then I need to get the expression for bending moment. So in the segment 1, I am taking a random section and I am considering that it is at a distance of x from the origin. Origin is B, so the distance is x. So what is the bending moment here? What is the bending moment? Force is RB, lever arm is x, so RB times x. And so the magnitude is RB times x. And what about the sign? Is it positive or negative? So that's the concept we have been discussing from the very second or third video itself. So this point is fixed. I'm applying the point load. The shape is sagging, which means it is positive. Okay, I got the expression for M in the first segment. Now I need to go for the second segment. Okay, I'm considering the second segment. So EI is again constant. Now I will be taking the section like this. So which side should be looked into, left or right? So left there are 3 reactions. In the right there are just 2, RB and 10. Okay, so it's better to look to the right. So I'm looking to the right and I will be getting the expression as, so what will be the X? Okay, so first let's decide what the origin is. So if I'm looking to the right, the origin can be either RB or this particular point. Any point can be taken as origin. I'm considering this as the origin. Okay, which means B as the origin. So what will be the limit? What will be the limit for segment 2? If this is 0, this segment will be, if this is 0, 2 to 4, right? If this is 0, this point is 2 meter, this point is 4 meter, so the limit is 2 to 4. So I'm going to get the limit as 2 to 4. Okay. And what about the expression for bending moment? So now I need to take the section in segment 2, and what should be x? X should be the distance from origin. This point is the origin. So now this is my x. Fine. So what will be the bending moment? There are two forces. So apply the Rajinikanth principle. Okay. There are two villains. Consider one villain at a time. So I'm considering the RB villain first. So what is the moment due to RB? RB times x. RB is the force. X is the lever arm. So RB times x. And I want to know whether it is sagging or hogging. So I fixed at where I'm taking the moment. I applied the force. Okay, the force at the free end, it's sagging. So plus. Now I'm considering the second villain. Second villain is the 10 kilonewton. So if I'm considering the section at here, what is the moment? 10 into the small distance. What will be the small distance? That small distance will be x minus 2, because this is 2 meter. So x minus 2 will give me this lever arm from the section to the point load 10. So the magnitude is 10 into x minus 2. Is that okay? How we got the value? You're taking the section here. So the lever arm is this small distance. This small distance is the lever arm. To get that, this is 2 meter. Okay. This distance is 2 meter. So total is x. X minus 2 will give me this lever arm for 10. Okay. So I'm considering the lever arm for 10. Fine. Now I need to check whether it is a sagging or hogging moment. So I consider the point as fixed and the load is applied at the center. The deflected profile is hogging, which means it is negative. Fine. So we have the expression for M in segment 1 and segment 2. That's all what we want. Okay. The only thing what we require as per this equation is the expression for M. So we got the expression for M in both the segments. Now we can directly apply this back in this very basic equation given by the theorem of least work. So I'm going to do that. So I'm going to substitute it. So this one, okay, here there's just one equation. It need to be divided into two segments. So I'm considering the first segment. First segment is having limit 0 to 2. Okay, limit is 0 to 2. M is RBX. Okay, so I forgot to add one more thing. So in this case, we require the value of dou M by, okay, so dou M by M. I'm not having enough space to write here. So I'm simply writing it this part here. Okay, you need to make the continuation. Okay, this is dou M by dou R. So in our case, R is RB. The redundant what we considered is RB. So dou M by dou RB. This table is actually continued here. Okay, you may be familiar with this notation. If you are not, this means that the continuation you will find here. Okay, so dou M by dou RB. So what will be the dou M by dou RB of this value? Okay, if I partially differentiate RBX, that is dou by dou RB of RBX, what will be the value? We know that it will be X. Okay, when I differentiate RBX in terms of RB, I will be getting X. Now what about here? When I differentiate this whole expression with RB, what will I get? From here I will get X. What about here? This is a constant. So when I differentiate a constant with respect to RB, I'm going to get it as 0. So here also I'm going to get the value as X. Fine. Is that clear? What I'm doing is I'm differentiating this parameter with respect to the redundant RB. So dou RBX by dou RB is basically X. And here from this I will be getting X. This becomes 0. So what I left is X. So I have these two values. Fine. Now we are going to substitute. So M is RBX multiplied by dou M by dou R. That's what we have calculated. For segment 1 the value is X. So X dx by EI. Fine. Plus, now I consider second segment. Second segment, the limit is 2 to 4. So 2 to 4. What is the expression for m? M is this long expression. I'm writing that. Rbx minus 10x plus 20. Okay, 10x plus 20. Then dou m by dou r. Dou m by dou r for segment 2 is x dx by ei. Okay, equal to 0 as per theorem of least work. Now when I calculate this integral, what will I get? Rb by ei is constant. Okay, integral x square dx. What is integral x square dx? It is x cube by 3 in the limit 0 to 2. Now here what will I get? So I'm taking the constant here. The constant is 1 by ei. Fine. Then what about this? There is an x that need to be multiplied. So the first term will be Rb x square. Integral Rb x square is Rb x cube by 3 in the limit 2 to 4, right? Minus 10x into x, that is 10x square. When I integrate that, I am going to get 10 into x cube by 3, 0 to 4, then plus 20x. So 20 into integral of x is x square by 2 within the limit 2 to 4 equal to 0. Okay, fine. So we got an expression. Is that clear? So I'm simply integrating it and I'm equating it to 0. So the limit is for segment 1 is 0 to 2, for segment 2 is 2 to 4. So all these terms, okay, whatever I have written here, all these terms are from segment 2 and this is from segment 1. Okay, this is segment 1, this is segment 2. So segment 2 when I'm integrating is polynomial integration. You can simply do that. So you are going to get an expression like this. Now let's see what is the values or what are the values. Okay, so I have this, keeping it apart, and I'm continuing it. So from the first segment, what we were having was Rb by ei. Okay, I'm putting it here so you will be able to see it. Rb by ei into x cube by 3. So I need to substitute x as 2. So what I'm going to get is 8 by 3. 2 cube is 8 plus, okay, I'm continuing, 1 by ei into Rb into again x cube by 3, but here it is, the limit is 2 to 4, that is 4 cube by 3 minus 2 cube by 3 minus 10 into x cube by 3. So 4 cube by 3 minus 2 cube by 3 plus 20 into x square by 2, which means 4 square by 2 minus 2 square by 2 equal to 0. Okay, now I just need to substitute the different values. So 1 by ei is common. I'm taking it outside. Okay, now here 8 Rb by 3 from here. What about here? What is 4 cube minus 2 cube? Okay, 4 cube minus 2 cube is going to give you the value. It's going to be plus 56 Rb by 3 minus 10 into again this term. So it's going to be 560 by 3, and this is 4 square minus 2 square. 4 square is 16 minus 2 square, which is 4. It's going to give the value 12. 12 times 20. Okay, 12 times 20 is 240 by 2 equal to 0. Okay, I'm just reducing that same expression. So we know that if the right hand side is 0, I'm just taking it to right, so EI goes away. EI into 0 becomes 0. So now I have an equation in terms of RB. Okay, the only unknown is RB, just one unknown. I can solve it. Okay, so what will this become? 56 plus 8 becomes 64. 64 RB by 3 minus, what about these terms? 560 divided by 3, that is 186.67 plus 240 by 2 is 120 equal to 0. Right? From this I can get the value of RB and just calculating it. So I'm taking it to the other side. 186.67 minus 120 into 3 divided by 64. So what I'm going to get is the value of RB is equal to 3.125 kilonewton. It is kilonewton because the load what we considered was in kilonewton. Fine. So I got the value of RB. Once I get the value of RB, I can substitute the value in the original beam what we considered. So the original beam is this one. Okay. This was 10 kilonewton. And I had a reaction from the roller or the prop, which is basically RB, and we got the value as 3.125. Okay. Now what is the system? Now this is a cantilever subjected to two loads, which means it is a determinate structure. Okay, because there are just three unknowns. If I am substituting this as reactions, what I am having is 10 kilonewton is acting here, and RB, that is 3.125 kilonewton, is acting here, RA, HA and MA. So now you can find in this given beam there are three unknown reactions, and for a beam we know that there are three equations of equilibrium. So R minus E is equal to 3 minus 3, which is 0. So now it is determinate, and you can simply apply the equations of equilibrium to get the three unknown values in this case. So I will use the basic equations of equilibrium, which we are dealing with from the very first semester, that is when we started to learn engineering mechanics. So for this beam I'm applying the basic equation of equilibrium. First I am trying with sigma Fx equal to 0. What will I get? There is a force HA. Is there any other force in the horizontal direction? Nothing is there, which means HA equal to 0. Now I'm trying the second equation, that is say sigma MA equal to 0. Okay, I'm considering moment with respect to this point equal to 0. So what are the forces causing moments? Okay, we have this as 2 meter, this as 2 meter. I'm taking moment with respect to this point. So there is an MA, and again I'm repeating the sign convention. Whenever we are going for summation, we don't have to think about sagging, hogging. We just need to think about clockwise, anti-clockwise. Whenever there is summation, clockwise, anti-clockwise. So you can see at this point there is a moment acting, which is MA, and it is clockwise, so which means plus MA. Then there is 10 kilonewton. Okay, 10, and the lever arm is 2 meter. So the magnitude is 10 into 2. Okay, what about the direction? Direction, again we can use the same principles. Okay, we use, so this is a point, the load is acting here and it is rotating in the clockwise direction, right? Because of the load it rotates clockwise, which means plus. Now there is a 3.125 acting at a distance 4 meter from the point A. So load is force is 3.125, lever arm is 4. So 3.125 into 4. Now I need to check whether it is a plus or minus. So when I consider this point, it is a anti-clockwise rotation, which means minus, equal to 0. Sigma MA equal to 0. From this I can get MA is equal to, let's calculate that. So 3.125 into 4 minus 10 into 2. So what I'm going to get is minus 7.5 kilonewton meter. Okay, kilonewton meter, that's the unit of moment. It will be normally force times distance or displacement. So minus 7.5. Why I got the value as minus 7.5? It means that the direction what I assumed for the reaction was clockwise. But in reality, the direction of MA is anti-clockwise. That's why I got it as a negative value. There is no problem if we consider it as clockwise or anti-clockwise. If the answer is negative, it means that the parameter is in the opposite direction. So you can assume it like anything. Just check the value. If there is a negative in the value, the assumed direction is wrong. Just revert it. If the what we are getting is positive, the assumed direction is correct. So here I got the value as minus 7.5, which means that the assumed direction of clockwise is not the right direction. This MA is actually in the anti-clockwise direction. Fine. Now I'm going for the next equation. What we have is sigma Fy equal to 0, because I already got the value of HA. I got the value of MA. The only unknown left is RA. To get RA, I'm applying sigma Fy equal to 0. So I'm equating the forces in the vertical direction. Okay, I'm considering the upward direction as the positive one. So there is RA upward, 3.125, that is also upward, and there is a force 10 kilonewton which is downward equal to 0, which means that RA is equal to, I'm solving it, so it is basically 10 minus 3.125, that is 6.875 kilonewton. Okay, so with this I have calculated all the unknown reactions in the given problem. Okay, if we are taking the first sheet what we were working on, we know that how many reactions were there? RA, HA, MA and RB. Now we can see that we have calculated the values of RA, HA, MA and RB, which are basically the 4 unknown reactions that we need to calculate. Once you have all these values, how to plot the BMD, SFD and all those things, you are already very familiar from the mechanics of solids. I'm not going into that part, okay, because there may be a sign convention issue. You may be plotting the bending moment to the compression side, I may be plotting into the tension side, so I don't want to create such a problem. So the reaction part is available. All the reactions are available. Now using these reactions, you can plot the BMD and SFD by yourself. Okay, so this is one basic problem. We'll practice few more problems so that this concept and this calculation part will be familiar to you. Okay, don't get afraid seeing lot of calculations here. Everything is based on that theorem of least work, that is dou U by dou R. Okay, the theorem of least work, that is dou U by dou R equal to 0. So identify the redundant, then get the expression for dou U by dou R from the table that we use for strain energy. We are not calculating the strain energy, but we are using the table, exact table, with an additional term which is dou M by dou RB, where RB is the redundant. And do this expression, okay, this expression we reformed into this form, okay, for the ease of calculation. If you are depending on this, then we may have to prepare the expression for the strain energy, that is integral m squared dx by 2a. This integration will have to be done. To avoid that complication, we reduce this equation into a format which is easier to handle, because if we have the expression for bending moment, we can use this condition. So this condition was used and I got an equation where the unknown was our redundant reaction RB. Okay, I substituted the values and I got the value of RB. Once the redundant values are known, the system become a determinate one. Then the solution part can be handled using the basic equations of equilibrium, that is sigma fx, sigma fy and sigma m equal to 0. Okay, and one more thing what I will suggest is that when you, after watching this video, you need to do it in a notebook. Okay, step by step, do it by yourself. You will get confusions. In between you may get stopped. Don't worry, just refer back the video, okay, and get the solution. And don't worry, we will be practicing more problems, so it is going to be pretty easy. You may even be able to solve such problems blindfolded. Okay, practice makes a man perfect. Okay. Thank you.